Welcome, everyone. I'm Oszkár Semeráth, and first of all, I would like to thank you for this opportunity for this presentation. Our work is about different graph generation techniques, and here my aim is to give a summary about a bigger research line with multiple collaborators. So, in summary, our approach aims to generate graph-based models. To illustrate our technique, we used a simplified version of a social network. In our example, a social network consists of persons which can be connected by a friend edge, and this is represented by a labeled graph with node labels and edge labels. Graph nodes labeled with posts represent posts of the persons, and graph edge with the reply to label represents a reply to connection between those posts. Models are frequently extended with data values like integers and strings. In our example, the network saves the date when the user joins to the network, or when and the creation time of the posts. Graph-based models like this are widely used in software engineering. They can represent system designs used in model-based engineering, the composition of pointers and objects in data structures, or the contents of a database, especially a graph database. Similarly, most testing, benchmarking, and design space exploration scenarios rely heavily on the construction of those graph models, which can pose a significant challenge. Therefore, to support the aforementioned techniques, we focused our research on the direct and automated generation of graph models that are consistent, realistic, diverse, or scalable. I'm assuming that a lot of you used or even developed different graph generation techniques for benchmarks. Here I want to present the challenge and opportunities of using automated model generations techniques which can automatically create such benchmarks, and they are domain independent. So let's discuss the functional overview of such a model generator. First, if we want to generate models, we need to specify the target domain. Typically, an industrial modeling language or the content of a database can be defined by a type graph or a meta model or a class diagram or something that lists the valid types in the model and the typical relations between them. Here I use the class diagram-like notation. The model generator is parameterized with additional requirements such as model size or expected distribution of types and labels and statistical properties of the graph. And if everything goes fine, it starts to create models that are instances of this type graph, valid instances of this type graphs, and satisfies all of the parameters that are given in the parameters. The generation of those models is a challenging mathematical task, which necessitates the usage of advanced mathematical algorithms and solvers in the background. Moreover, we are aiming to provide a generic domain-independent generator, which can provide graphs, or at least partial graphs, for various testing and benchmarking scenarios. So, which makes this problem much more difficult. In the following, I would like to present the characterization of such model generations, and to characterize this ideal model generation or graph generation technique, we specified the core disk model, and which consists of 4 properties, and I will talk about those properties, and I will try to quickly summarize our state of the art in this with respect to those graph generation properties. The first property is consistency. So what this consistency means? To control the range of valid graphs, modeling environments are frequently extended with well-formed constraints. For example, in real models, the timestamps of the reply post must be greater than the original post to satisfy this consistency criteria, or not consistency. We would like to get models where this constraint is respected. Otherwise, we may get strange results from a benchmark, which, for example, tries to order those posts into some kind of list or queue. Similarly, models typically have certain structural constraints. For example, the friend relation must be symmetric. Those constraints can be captured as graph predicates or alternatively model queries or database queries. If we use those queries, the integrity of an existing models can be checked, and we can use those queries as an input for the model generation to ensure that the models that we get will be valid. It's easy to see that if a generator provides random models, it could invalidate the results of tests. And if we generate random models, we have no hope to generate models with 0 errors from those, even from those simple constraints. So, in summary, what is we call a model generation correct with respect to consistency if it generates models that satisfy all constraints. So, if we illustrate the valid models or consistent models with this blue square, the generator will provide models that are inside this square and won't generate models outside of this. Similarly, we can define completeness, which tells that a generator can eventually provide all of the consistent models that are valid. And if we run this generator long enough, it will list all of the valid models. Of course, in a complete model, we can generate other models as well. What's the state of different benchmarks? So benchmarks are typically starts to generate models, and if we increase the parameters or we change the parameters a bit, it can generate a sequence of different models, but that are typically consistent or correct. But the goal is not to generate complete set of models or sample in the set of consistent models. If a model generation technique is correct and complete in the same time, we can say that this generator is consistent, which is a very challenging task, which necessitates the usage of different logic solvers than like SAT solvers or SMT solvers. And this can be a very challenging task. To support the generation of consistent models, we created some specialized algorithms that scalable, and it can generate those valid models. as a comparison, again, I just want to show you a quick overview of our results compared to the state of the art. If you are familiar with Alloy, which is a set solver based graph generator, we conducted some measurements to compare the size of the models that we can provide, and it shows that our generator can provide models with the objects in the range of thousands, while Alloy and Z3 and Formula and other tools are typically way below 100 nodes. If we compare the runtime of those solvers, we can see that our solver is almost all like those solvers are failing with model size. And of course, we can see that this is 2 orders of magnitude larger. Those numbers are not in the range of database benchmarks, clearly, but at least models with thousands of objects could be used as fragments of the benchmarks, or multiple models can be glued together eventually, or they can be used potentially in benchmarks, which might not be the case with traditional or traditional logic solvers. Okay, let's move to the realistic nature of models. We say that a model generator is realistic if we cannot distinguish the models it generates from real ones. Of course, first of all, we focus on the graph part of the models or the database contents here, so we can ignore the labels. So we don't care if the persons have the names of generated 1, generated 2, generated 3. We just need to see the big picture of the distributions. So we say that a generator is realistic if it generates models that are following are following the distribution of real models. Additionally, we can check the distribution of all models or multiple models, and we can say that the set of generated models is realistic if if the set is close to a set of real models as well. In custom benchmark generators, this realistic nature is ensured manually, and our goal is to use a set of real models, learn the metrics from them, and try to imitate the generation of real models. And what is the state of the art here? First of all, we measured several graph metrics to characterize real models that are available. And here is a paper of that. And we configured our graph generator to construct models with the same metric values. Here we used, in this example, we used multiplex participation coefficient. And this is just an illustration of our measurement. Here, this is a very complex diagram, and I don't really want to explain every details, but here the goal was to generate the orange cloud of dots close to the yellow one. And go forward. Similarly, diversity is another important problem. We say that a model generation is not diverse if it generates very symmetric models, for example, copy-paste models, which is frequent in manually created benchmarks. And additionally, we can use this diversity to characterize a set of models where any pairs of models is in a different equivalence class with respect to some equivalence classes. And this is critical for testing graph processing systems. And again, we propose some diversity metrics, and we observed that those metrics are highly correlate with mutation score, which is a metric for characterize a test set. And if we compare manually created models that are in between diverse models and non-diverse models, so manual models are not diverse, and we need specialized generator if we want to generate diverse models. And finally, scalability is the last property. We say that a generator scalable in size if it can generate huge models, and it's scalable in quantity if the generation time of the next model that does not grow if we generate a sequence of models. We have seen a lot of properties, and it can be hard to guess the interaction between those different properties. For example, consistency can be very challenging, and this can give us an upper limit for the model size. And we can see that if we have large inconsistent models generated by another approach, models cannot be transformed or healed into consistent ones. So I would like to summarize my presentation. We provided a framework for generating different graph models, and those algorithms are available in the Viatra solver framework. It gets standard EMF models, which are modeling standards for describing graph models as an input, and it can generate graph models as output, and we can visualize them or as GraphML or in other techniques. For structural reasoning, we are using Viatra query, which is an incremental query engine developed for models and modeling environments. And for numerical reasoning, we are using the Microsoft Z3 SMT solver. We have used those model generations to help testing modeling environments for aircrafts. Currently, we are generating different challenging traffic situations for autonomous vehicles, for testing autonomous vehicles, and we were able to generate different railway topologies for the reliability analysis of railway switches. And our tools are available at this link. And thank you for your attention.
Thanks, Oszkár. Any questions from the room or online? Domagoy has his hand up, so let's go ahead, Domagoy.
Hey, thanks. Thanks for the presentation, Oszkár. Nice tool. So, question, I didn't get this but do you actually, can you control the distribution of the outgoing vertices based on the nodes?
Yeah, so if we want to, we have multiple ways, of course, we have multiple ways to control the outgoing vertices. So first of all, we can define a consistency criteria that, for example,
Wait, okay, sorry, I think you didn't get my question, I guess. Yeah. So my question is like this: will the benchmark generate one node that has 10 outgoing edges with the label nodes and the other node that has 10 million? Can you control these type of things?
Yeah, if we have strict rules to control them, those are consistency properties. And additionally, we can define them as a statistical property, and our generation technique will
so you can
follow this distribution.
So you can put a random variable on the something like a edge distribution, right?
Yeah, and we used those previously in our measurements. So we were able to generate like GitHub models with the same outgoing edge distribution that are So we generated users and commits and stuff like that with the same distribution as GitHub provided.
Okay.
So some users had just a few commits, and other users had like hundreds.
Yeah, cool. Yeah, nice. This is very useful.
The size was not in the millions, but in the few thousands.
Okay, yeah, I guess it's more difficult to control consistency than everything. So yeah. Thank you.
Any more questions?
Yeah, what are, so yeah, a few thousands, that's not very much. So so what are the scalability limits of this?
Yeah, sure. It's not that much. So our observation is that the most important property is typically the consistency. So if we generate models that are inconsistent, we can improve the scalability of realistic generation, but we will have some parts of the models which have some strange anomalies. And the satisfying the consistency is this challenging numerical logical task which needs logic reasoning, which is at least NP-complete, and often.
Can you attempt a concrete answer to my question? I understand this is difficult.
Yeah.
NP-complete. So the question was how scalable this is. So how big a graph can you generate?
Yeah. So at most 10,000 with the current tooling. Okay. 10,000 nodes and edges.
Okay.
As much as necessary.
Not really very large database material.
Yeah, sure. The question is whether if we generate a model with 1,000 objects, and we generate like 1,000 of this, can we connect them together to create a larger benchmark? Because if we need to generate one large model with
now the answer is no, because
yeah, sure.
You could make the union of these smaller benchmarks, but that would have a really strange graph shape that would certainly not be consistent.
Yeah, that's true. That might be true for example, GitHub. Like we generate one day of commits.
Yeah. If you have a graph that consists of very many small very many unconnected graphs, then you could do that indeed.
Yeah, sure. We experience the same thing. Unfortunately, currently there is no reasoning tool to generate more. Like the other tools generate up to 50 or at most 100 objects. This can be an extremely difficult task if we want to ensure the well-formed constraints.
Well, there may also be other methods to achieve the same purpose. Maybe cutting some corners.
Yeah, we are experimenting with giving hints to the graph generator. So if you know the domain and you know how models are constructed, then you can specify rules to help this whole process. But if you want to automate everything, that might be the current state of the art.
Okay.
The 1,000, unfortunately.
Well, apparently I'm a co-author on this work, so I can also chime in, even though I didn't do much in the last 5 years. These models are excellent for testing, so they can really reveal the corner cases and torture the system under test in that regard. So definitely for testing, these sizes are usually sufficient. So that's definitely one use case where this approach shines.
Oh, sure.
Okay. Again.
Martin has his hand up. Yes, Sorry, I didn't realize that we're almost done. Like I want to second your last comment. Like, so we've been very interested in test data generation as well, not necessarily for performance benchmarking. And like, if you can generate valid worlds in the set of constraints, then you can do a lot with, let's say, testing that other implied constraints or assumptions work, right? So this is very useful work. We really appreciate Alloy. And if you already can handle more constraints and better scalability than Alloy, that's already tremendously helpful. But it's kind of orthogonal from performance benchmarking, maybe. So so we're very interested in it. Yeah.
We were able to generate performance benchmarks for modeling environments. So, of course, handling a state chart. If you want to store a state chart with 10,000 states in a database, is not challenging. But if you want to measure the performance of a code generator, which starts with a state chart with 1,000 states or 10,000 states, that can be challenging. So
maybe also a quick comment to riff on what Martin said. So you can sort of control the scalability of the model generation process by reducing the expressivity of the constraint language, right? So Yannis had work in ASC 2007, Yannis Maragdakis, where he showed that if you have a slightly less rich constraint language, you can have basically linear or polynomial time test data generation, right? Yeah, so you trade off the richness of the constraints with the kind of scalability you need. Sure. In our work, we focused more on first order logic, so the complete first order logic predicates, because it's very hard. If you have a limited expression power, it needs only a single constraint that will violate it. So if you have a very simple constraints and you generate a very large model, you will see an example, at least a single example for that violation.